continue from previous video where we find the bottom reinforcement at the midspan in the beam. I can show it to you here in a minute, but now we need to find the reinforcement at the continuous span. So if I just show it to you in a figures in the questions, so we are working with this slab. We found the reinforcement here at the midspans. Now we need to find the reinforcement at continuous. So over here, that's we are working on, and that is the negative moment regions hogging, and we need to provide the top tensile reinforcement here. So for that one, we're going to use the same equations, 5 mu greater than m star. If you we follow exactly the same procedure that we just done for the bottom reinforcement. This mx stars is the change because as you can aware that one that at this particular point we have found the value of minus mx star, that is the negative moment was 18.6. so this for this moments, how much reinforcement required for this continuous support. So we are going to, instead of 14, we're going to use 18.6. so exactly the same procedures that's shown here, but instead of 14 kilonewtons here we're going to use 18.6. so I use exactly the same notation that I copied here. I explained you this one in the previous video, but just instead of 14 I put 18.6. so that allow us to put 433 millimeters square. That makes sense, right? Because you can see here you did 326, so here you need 326 millimeters square, but for 14 kilonewtons you have higher moment here, which is almost 19 kilonewton meters. You need more reinforcement here. That makes sense, right? The calculations, mathematics makes sense here. So far we calculate at the midspan, at the bottom reinforcement you need 326. So we need 326 here at the midspan. At the supports you need 433 millimeters square. Now we also need to provide the reinforcement here at discontinuous edge. So for that discontinuous edge we will have same thing, same equations that are used here, but instead of 14s we're going to use 7s. In the last previous videos we calculate the 7 kilonewton meters. That was the moment, negative moment at this discontinuous edge. We call that spandrel beam at a discontinuous edge. Exactly the same procedures, but instead of 7 we will have this 162 millimeters square per meters. And if you compare three of them, you can see this moment is small, that is little higher. So we have a respective reinforcement, highest reinforcement here for higher moments, and then you have 326 and you have this 162 millimeters square per meter. And please note all these one are based on this 1 meter strip. Okay, so that is the at midspan we provide the bottom tensile reinforcement, at the supports we provide the top reinforcement here, and this is also again at that discontinuous edge. Now there is one more requirement that I just like to emphasize here. So let me redraw these pictures here, and I just redraw this. If I looking from this side 5 meters, I redraw this beam here, then you have this span, and then you have this beam here that I draw, and then you have continuous. We are working on this one, so I put those notes here that we just calculated. At the midspan we were calculated 326 millimeters square per meters. So at the midspan you need 326 millimeters square per meter. At these continuous supports you need 433 millimeters square per meters. I think I have a missing detail here. That should be per meter. So that is 433 millimeter per meters. At these supports here you need 162 millimeters square per meter, that are basically following our moment bending moment diagrams. That's the calculation. Now Australian standard has a minimum steel requirement. So anywhere in the beam, regardless where the beam is located, regardless whether you are designing here or anywhere of this slab, it has a minimum reinforcement requirement. So we need to make sure that this reinforcement that we are providing, it is satisfying the minimum steel requirement that is given in the clause 9.1.1 A and B. Okay, A slab, when your columns when your slab are supported on the column. So if you are thinking of the slab and you have just 4 corner columns, then you use this A. But here our slab are supported by beams and wall on the 4 sides, so we have a slab supported. So we're going to use these equations, that is AST on BD, minimum AST on BD greater than or equal to this I copied here. I redrew these pictures here. If you noted that depth of the slab is 150 millimeters, I think I can show it to you here that in the previous steps we found that 150 millimeters, and we have this small d 119. That's I redraw it here. Now one more parameters that are missing here, that is fct dot f subscript ct dot f prime. That is the tensile strength of the concrete. If you go all the way to the front of the standards on page number 44, you can find on clause 3.1.1.3 as fct dot f star is equal to 0.6 fc square root of fc dash. So copy that equation here, 0.6 times square root 32. Now the megapascal 32 concrete compressive strength given in our examples, take fc dash equal to 32 megapascal, that is given in our questions. Substitute that 32 megapascals, simplify, give you 3.4 megapascal. So if I substitute this AST in this equation, B, please note B is 1000 millimeter, that the strip that we assume, so that is in the millimeter. D 119 millimeters, I can show it to you again here. We have done the calculations, 119 millimeters, that is the D. Greater than or equal to 0.19. Capital D is the depth of the slab, 150 millimeters. I think in the previous videos we found that was 150 millimeters based on that trial depth. Over D 119 square times fct dot f, we just found 3.4. Yield strength of N bars, I show you in the last video, 500 megapascals. So if you simplify that, is 244 millimeters square. Now for the whole slab, this is independent of where your slab is located. If you are designing at corner or in the middle or in the side, anywhere you are designing it, this AST should be independent where your slab located. So we need to reuse this value and recheck this AST value for everywhere. Let's check it here. Alright, let's do it here. 433 millimeters. Yep, that is okay, because 433 is greater than 244. That is okay. Check, that is okay. There we can use 433 millimeters per meter here. If you check at the midspan, so that should be okay, we can use it. If you check it at the midspan 326 millimeters square per meters. Yep, it is greater than 244 millimeters square meters. That is okay, so we can use this 326. But here is very small, 162 millimeters square per meter. Now standard says that you can't use this 162 millimeters square per meters. You must have at least 244 millimeters square. So we can use, instead of 162, we can use 244. That would be correct. But then for this different spacing, it is very uneconomical, or it costs more to have a different spacing. So what we have done, let's take the same spacing or same area, that 326 here, 326 here instead of 244. If you provide more, is better. So that is, they still satisfy 244. So we just take this value 326 millimeters square here instead of 162. That 162 we are not using because it's not satisfying the minimum still requirement of clause 9.1.1b. So therefore we change that 162. We could change this one to 244 millimeters square per meters, but it would not be economical to use different steel area for different supports and many different detailing. Rather than that, we can use this 326 millimeters square per meter in this zone. In the next video, we will check the creep and shrinkage requirement for the standards in the next video. Thank you.